Good afternoon, everyone. Welcome to the webinar series on managing drought in the Southern Plains. I am Margaret Boone. I'm the program manager with the Southern Climate Impacts Planning Program, and I will be the moderator for today's webinar. We are joined today by Jason Otkin from the University of Wisconsin-Madison, Martha Anderson from the USDA Agricultural Research Service, and Mark Svoboda and Brian Wardlow from the National Drought Mitigation Center, who will be talking about a new drought monitoring product, the Evaporative Stress Index, or ESI. You may notice a different format for the webinars. Skip has been producing 5-minute briefings on the drought status and outlook and posting these periodically to the Skip videos website on southernclimate.org. This allows us to streamline these webinars to focus on a particular topic or issue, which should shorten them to about 30 minutes. This is part of an ongoing series made possible through the support of several organizations, including the National Drought Mitigation Center, National Integrated Drought Information System, NIDIS, and NOAA Regional Climate Services. We also greatly appreciate those of you who join us in this webinar series and recognize the valuable time that you commit to participating. You may ask questions or make comments at any time through typing in the chat box. We will address these questions at the end of the presentation. Each of these webinars is recorded and posted on the Skip website, southernclimate.org, or on our Skip YouTube channel. You can also friend us on Facebook or follow us on Twitter at skip_RESA. I will now turn it over to Jason Otkin to tell us about the Evaporative Stress Index.
All right, thank you. My name is Jason Otkin. I work at the Cooperative Institute for Meteorological Satellite Studies at the University of Wisconsin-Madison. Before I go into the webinar, I first want to say that funding for the projects I'm going to describe today was provided by the NOAA Climate Program Office and also by the U.S. Department of Agriculture. Next slide, please. In the first part of the webinar, I'm going to describe some of the characteristics of flash drought events, which typically occur during the summer and can intensify very rapidly. After this first section, I'm then going to describe the satellite-based Evaporative Stress Index and illustrate its potential use of the drought early warning tool. As we'll see later in this talk, the ESI can be used to identify areas of vegetation experiencing moisture stress conditions across the United States and can provide early warning of flash drought development. At the end of the webinar, I'm then going to discuss results from 2 focus group meetings that were held last year with stakeholders across the central United States to better understand how they could use drought early warning information to prepare for worsening drought conditions and also to reduce its negative impact on their operations. We also request your input on ways to improve the usefulness of the ESI within the agricultural community. A link to an online survey will be provided at the end of the webinar today. Next slide, please. Okay, so what exactly is flash drought? Most people tend to think of drought as being a slowly developing climate phenomenon that takes many months or even years to reach its full intensity. However, as we've seen across the central United States in recent years, drought onset can actually be very rapid, especially when extreme weather anomalies remain over the same area for several weeks or months. Research has shown that flash droughts are more likely to develop when intense heat waves combined with below normal rainfall, strong winds, low humidity, and sunny skies to quickly deplete the root zone soil moisture content. These weather features can lead to the rapid emergence of agricultural drought conditions, even when rainfall departures are not especially large, because each one of them can increase moisture stress in vegetation. This means that moisture-related stress can increase very rapidly when several of these weather features occur at the same time, which can then lead to rapid onset flash drought development. Next slide, please. Drought can be defined both by its intensity and by its duration. An intense flash drought that develops very quickly can impact agriculture more than a slower developing but longer lasting drought event. For example, crop yields can be greatly reduced if flash drought occurs during a sensitive stage of crop development, such as pollination of corn or the filling stage of soybeans. The initial impacts of flash drought are often observed in pasture and range conditions as the vegetation rapidly browns and goes into dormancy, and then visible signs of moisture stress appear later in other crops and vegetation. During flash drought events, evaporation rates can be up to 2 times higher than normal, which means that an inch of rainfall that may have been sufficient to provide enough soil moisture to last for a week under normal conditions would instead last for only a few days under these more extreme conditions. The soil moisture content can be depleted so quickly that the vegetation rapidly becomes moisture stressed during a flash drought event. Next slide, please. Okay, this slide shows the evolution of the flash drought event that impacted eastern Oklahoma and western Arkansas during 2011, as depicted by the U.S. Drought Monitor, which is a state-of-the-art analysis system that combines information from many different data sources to produce a unified drought analysis each week. I want to point out that the darker colors on these images depict the most severe drought conditions for each of those times. You can see that conditions were generally good across the region at the beginning of June. However, drought conditions rapidly intensified during the next 2 months, with some locations experiencing up to a 4-category increase in drought severity over a 6-week time period. This means that areas that were free of drought at the beginning of June actually found themselves in severe to extreme drought conditions only a few weeks later, which is extremely rapid drought development. Next slide, please. This slide shows the flash drought event that impacted the central United States during 2012. As you can see in the top left panel, conditions were generally good across most of the region at the beginning of May. However, dry weather caused drought conditions to begin to intensify by the first week of June. Exceptionally hot and dry weather then developed across the region during June and persisted until the middle of August, which then contributed to flash drought conditions being able to rapidly develop. For example, eastern Nebraska and southern Wisconsin went from being drought-free at the beginning of June to having extreme to exceptional drought conditions by the end of July. Now, further to the south, across central and eastern Oklahoma, they also went from having good conditions at the beginning of June to having exceptional drought conditions only 2 months later. And this, in fact, was the second consecutive year that parts of Oklahoma experienced flash drought conditions. Next slide, please. Okay, this slide shows before and after pictures of a natural grassland located in central Oklahoma during the 2012 flash drought event. You can see in the left panel that the grass was relatively green at the beginning of July, but that it had turned completely brown and most likely had entered dormancy by the 7th of August as drought conditions rapidly intensified, and this is shown in the right image. The seasonal browning of grasslands in this part of the country is certainly not unusual, but the speed with which this occurred during 2012 was unusual and seems to be representative of flash drought conditions. Next slide, please. Okay, so now I'm going to spend a few minutes describing the Evaporative Stress Index and its use of the Drought Early Warning tool. To provide some context for this discussion, this slide shows a comparison of the Evaporative Stress Index and U.S. Drought Monitor analyses near the peak of the 2011 and 2012 flash drought events. The red colors on the ESI images on the left indicate drier than average conditions, and the green colors indicate wetter than average conditions. So overall, you can see that the Evaporative Stress Index and Drought Monitor analyses have similar spatial patterns near the peak intensities of both of these flash drought events. You can also notice the very high spatial resolution of the ESI datasets with spatially continuous observations available across the entire United States every 2.4 miles in distance. Next slide, please. Okay, so fundamentally, the Evaporative Stress Index is used to depict anomalies in evapotranspiration, which represents the total moisture transfer from the soil to the atmosphere due to a combination of evaporation from the soil surface and transpiration from vegetation. Typically, if vegetation has access to sufficient soil moisture reserves, the amount of water vapor it releases through transpiration will increase in response to greater atmospheric demand associated with things like hot temperatures, sunny skies, and strong winds. However, the vegetation is moisture stressed, it will be unable to cope with the higher atmospheric demand and will instead begin to show signs of moisture stress, such as curled leaves and corn. Now, in this situation, the vegetation will give off less water vapor than would have otherwise been expected based on the atmospheric conditions. This then means that the actual ET is less than the expected or potential ET when vegetation becomes moisture stressed. Next slide, please. The evaporation or the evapotranspiration values used to compute the Evaporative Stress Index are obtained using satellite thermal infrared observations and a land surface energy balance model. This graphic shows how solar radiation at the Earth's surface is used to heat the soil by a ground heat flux, heat the atmosphere by a sensible heat flux, and evaporate water through transpiration from vegetation and evaporation from the soil. Prior studies have shown that land surface temperatures derived from thermal infrared imagery can provide a reliable signal of incipient drought stress that may not be evident using other drought monitoring tools. The reason for this is that as the root zone soil moisture decreases, the canopy temperatures rise in comparison with unstressed vegetation because less energy is being used to evaporate water, and instead more of it is used to heat the surface through sensible heat fluxes. What this means is that temperatures will be higher for plants experiencing moisture stress than it will be for plants that have sufficient soil moisture to meet the atmospheric demands. And it's this relationship between increased moisture stress in vegetation and of higher canopy temperatures that can be detected using satellite thermal infrared imagery. Next slide, please. Two values are required to calculate the ESI. These include the potential ET and the actual ET. The potential ET represents the maximum evapotranspiration that would occur for a given set of atmospheric conditions if the vegetation were able to access enough soil moisture to meet the atmospheric demand. The potential ET is calculated using the observed temperature, water vapor, wind speed, and solar radiation at the surface. The actual ET is then estimated using a land surface energy balance model and satellite thermal infrared observations, and then drought severity can be inferred through reductions in the ratio of the actual to potential ET when compared to the climatological norms for given location and time of the year. Now, by computing the departure from these average conditions, this then means that negative ESI values indicate drier than average conditions, whereas positive values will indicate wetter than average conditions, again for a specific location and time of the year. Next slide, please. Okay, one of the main limitations of the ESI is that in its current form, it can only be computed for locations that have clear skies, because thermal infrared imagery will be unable to see to the surface when clouds are present. This means that there could be a long time period with no new evapotranspiration estimates if cloud cover persists for an extended period of time. To produce more complete domain coverage, however, we typically composite clear sky ET estimates over longer time periods, such as 2, 4, and 8 weeks, and then use those longer-term composites to compute the evaporative stress index. I want to point out that we are currently developing techniques that can fill in these cloudy regions using satellite data collected in microwave radiation bands, which are able to see through clouds and thus can see all the way down to the surface. There are also several advantages to using the ESI as a drought monitoring tool. One of these is that the ESI provides spatially continuous observations of moisture stress across the entire United States, with observations available every 2.4 miles, so very high resolution. Perhaps the most important benefit of the ESI, though, is that it is highly sensitive to rapid changes in soil moisture conditions, because the energy balance approach used to estimate ET can account not only for the impact of dry weather and vegetation, but can also account for the impact of hot temperatures, sunny skies, and strong winds that often occur during flash drought events. This drought early warning capability makes the Evaporative Stress Index a very useful tool with which to detect the rapid emergence of flash drought conditions. Next slide, please. Okay, the next thing we're going to do is to look at how the ESI and other data sets changed during the flash drought event that occurred across eastern Oklahoma and western Arkansas during 2011. This slide shows the U.S. Drought Monitor 4-week ESI anomalies and monthly rainfall totals at the end of April, May, June, and July. In the middle column, the green colors indicate locations where the ESI is showing wetter than average conditions, and then the red colors indicate drier than average conditions. So in the right column, you can see that very heavy rainfall occurred during April and May across this region. However, much drier conditions then developed during June and July. The spatial patterns in the ESI and U.S. Drought Monitor closely match each other during April and May during the wet conditions. However, they began to diverge by the end of June as dry and hot weather became more entrenched across the region. The large negative ESI anomalies at the end of June indicate that extreme moisture stress had already developed across the region by that time, even though conditions were generally good just a few weeks earlier. The U.S. Drought Monitor depicted rapid drought development during July. However, it's important to note that this period of rapid drought development occurred several weeks after the initial appearance of the large negative ESI anomalies, which indicates that the ESI provided early warning of drought development during this flash drought event. Next slide, please. Okay, this slide shows time series of daily surface meteorological conditions averaged over eastern Oklahoma and western Arkansas from the end of May until the first week of August. The top panel shows anomalies in surface temperature in black, dew point depression in blue, wind speed in red, and cloud cover in green. The bottom panel shows the rainfall departure in red. The U.S. Drought Monitor is in black, and then the 2, 4, and 8-week ESI anomalies are shown in blue, green, and yellow. All of the variables in the top panel, along with the rainfall departures in the bottom panel, can be considered to be the drivers of this flash drought event, with the other variables in the bottom panel then depicting the response of the vegetation to the anomalous weather conditions. So if you go back to the top panel, you can see that hot and sunny conditions had developed by the beginning of June and then persisted almost without interruption until the first week of August. The very high evaporation rates due to the hot sunny weather were further enhanced by the unusually strong wind speeds that further depleted the red zone soil moisture content. Now, in the bottom panel, you can see that the ESI anomalies were already becoming negative by the end of May, with the first large weekly decreases occurring during the second week of June, even though there was still a large rainfall surplus at that time. It wasn't until several weeks later before the U.S. Drought Monitor began to depict rapid drought development. Now, the reason for the apparent discrepancy between these drought indicators is the way in which that heavy rainfall was received during April and May. It was associated with very intense thunderstorms with very high rainfall rates, which meant that much of the rainfall simply ran off into area rivers rather than being able to recharge the subsoil surface moisture content. This then meant that the vegetation remained more susceptible to drought conditions than may have otherwise been expected based on the rainfall totals alone. Next slide, please. Okay, next thing I want to do is to show a new visualization tool that we developed that we refer to as a plume diagram that's used to display information from multiple data sets on the same image. It's organized so that time moves downward from March at the top to the end of October at the bottom. The first three columns show the U.S. Drought Monitor, weekly rainfall totals, and the standardized precipitation index. The next three columns show the 2, 4, and 8-week ESI anomalies. And then the last 12 columns on the right show change anomalies depicting how rapidly those ESI composites are changing with time. With these change anomalies, red colors indicate conditions are deteriorating rapidly, whereas green colors indicate conditions are improving rapidly. This slide shows conditions, again, averaged over eastern Oklahoma and western Arkansas during the 2011 flash drought. So overall, you can see that conditions had improved during April and the first half of May in response to the heavy rainfall that occurred during that time period. However, large negative ESI change anomalies had already developed by the end of May, which shows that conditions were already beginning to deteriorate, even though the U.S. Drought Monitor still indicated conditions were generally good at that time. Again, it wasn't until several weeks later before the U.S. Drought Monitor and Standardized Precipitation Index datasets indicated rapid drought development. These results again demonstrate that a flash drought can develop even when there are long-term rainfall surpluses. And as we saw in the previous slide, the rapid decrease in the ESI anomalies occurred when dry weather was accompanied by hot, sunny, and weather conditions that together caused drought to rapidly develop across the region. Next slide, please. Now, because anomalous weather conditions supportive either drought development or drought recovery can persist for many weeks, large ESI change anomalies can also occur for an extended period of time as the vegetation responds to sustained changes in moisture stress conditions. This means that it may be useful to assess not only the magnitude of the ESI changes each week, but also their accumulated magnitude over longer time periods. So to account for this behavior, we developed a new drought metric that we refer to as the Rapid Change Index that captures the total moisture stress change occurring during the full duration of a rapid change event. The RCI is designed so that it can be used to identify areas experiencing either rapid increases or rapid decreases in moisture stress conditions, with negative values indicating increasing moisture stress, whereas positive values will indicate improving conditions. Next slide, please. This slide shows the evolution of the 2012 flash drought event across the central United States. The first column shows the 2-week rainfall totals. The next two columns show the ESI and RCI. And then the last column on the right shows the U.S. Drought Monitor. After experiencing record warmth during the spring, Abnormally dry conditions were present across most of the region by the beginning of summer, as is indicated by the U.S. Drought Monitor and also by the large negative ESI and RCI values at the beginning of June in the top row. Extremely hot and dry weather during June and July then led to rapid drought development across the region. The important thing to note here is that the initial appearance of the large negative RCI values at the end of May and the first part of June occurred several weeks before the U.S. Drought Monitor depicted rapid drought development. And this provides some additional evidence that rapid changes or rapid decreases in the ESI, as depicted by the Rapid Change Index, can provide useful early warning of drought development. Okay, next slide, please. Okay, the next thing I'm going to do is to show two examples that demonstrate the relationship between the ESI and corn yields across the United States. This slide shows conditions during the 2012 flash drought. Now, in this case, the first column shows the U.S. Drought Monitor, the middle column shows the ESI, and the third column shows topsoil moisture anomalies compiled by the U.S. Department of Agriculture. The image on the far right shows the percent reduction in state average corn yields during the 2012 growing season compared to the long-term trend. Now, you can see that corn yields were greatly reduced across the U.S. Corn Belt, with yields generally less than 80% to normal in most of the states. The largest yield reductions occurred across the western and central Corn Belt in areas that were hardest hit by the drought. Overall, you can see that there is a strong relationship between the severity of the drought event, as depicted by the Evaporative Stress Index, and the areas with the largest corn yield reductions. Next slide, please. Okay, this slide shows the correlation between the Evaporative Stress Index and end-of-season corn yields during various stages of the growing season. Positive correlations indicate that corn yields at the end of the growing season will be higher than normal if the ESI is positive, but will be lower than normal if the ESI is negative. So overall, you can see that the correlations are relatively small at the beginning of the growing season, on the left side of this image, but that they increase substantially by the middle of summer. What this indicates is that moisture conditions at the beginning of the growing season only have a minor impact on the final corn yields, but that their impact becomes larger as the growing season progresses. For example, the correlations for Illinois and Indiana increased to more than 0.5 by the end of June. The high correlations for many of these states mean that by the middle of summer, if the ESI is negative, there's a pretty good chance that corn yields will be lower than normal, but if the ESI is positive, then corn yields may be higher than normal. This is potentially very useful information that shows the direct relationship between moisture stress, as depicted by the ESI, and the end-of-season corn yield. Also note the vertical line at the end of July that shows when the first yield forecast is released by the U.S. Department of Agriculture each year. The high correlations in many states prior to the release of this initial yield forecast indicate that the ESI may also be useful for marketing decisions, since it could be used to anticipate final yields and also give some indication for what the initial USDA yield forecast will be. Okay, next slide, please. Okay, so the last thing I want to discuss today are results from two focus group meetings that were convened with stakeholders in the Nidus and Southern Plains and Missouri River Basin pilot regions last summer. The primary purpose of these meetings was to better understand how the attendees could use the drought early warning information provided by the Evaporative Stress Index to reduce their drought risk, and also to solicit feedback from the attendees that could be used to improve how this information is shared with the end data users. All of the attendees were invited based on their prior interest in drought management, with a total of 30 people with diverse backgrounds attending both meetings. Overall, 70% of the attendees were researchers, 20% were from state and local government, and 10% were full-time farmers or ranchers. And more importantly, most of the attendees were either directly or indirectly involved in agriculture. Each meeting included an interactive discussion of flash drought events and the societal impacts, and the several presentations were used to introduce the attendees to the ESI and associated drought monitoring tools such as the Rapid Change Index and ESI change anomalies. Next slide, please. Okay, so the attendees, some of whom were shown in this picture, were asked to assess the utility of these data sets as drought early warning tools through a combination of group discussions, analysis of recent flash drought events, and a written questionnaire that was provided at the end of each meeting. Next slide, please. Okay, so during each meeting, the attendees used the ESI change anomalies, and RCI data sets to analyze the evolution of several drought events. These data sets were presented to them either as separate domain maps for each variable and time, or as part of the plume diagrams that I showed earlier that combine information from multiple data sets into one image. Overall, most of the attendees had a favorable opinion of the ESI and RCI variables, with 89 and 68% approval for each of these data sets. The attendees generally preferred to view these data sets in map form over large spatial areas when assessing current drought conditions, and found them to be most useful when used together because the ESI shows the current drought conditions, whereas the RCI shows how conditions have been changing in recent weeks. The feedback was less favorable when assessing the ESI change anomalies because many attendees found them more difficult to interpret. Now, in general, the attendees preferred to use the rapid change index, even though it's computed using the ESI change anomalies that they did not like. This data preference indicates that the rapid change index methodology adds value by transforming those ESI change anomalies into a more easily understood format. Next slide, please. Okay, so the attendees were also asked to describe how access to improved drought early warning information would affect their decision-making process. For ranchers, early warning of worsening conditions would allow them to preemptively move livestock to different pastures or to purchase supplemental feed. Farmers indicated that drought early warning information could affect their marketing decisions and could also help them decide whether or not to plant a cover crop after harvest. It was also mentioned that the incorporation of additional drought early warning indicators in the U.S. Drought Monitor could potentially lead to earlier drought declarations because most state and federal drought declarations are based on when the U.S. Drought Monitor reaches a certain intensity threshold. This then means that the sooner the Drought Monitor can get to a certain intensity, the sooner government assistance can be requested. This could then potentially lead to more timely government drought relief measures, especially during flash drought events. Next slide, please. Okay, so finally, we also request your input regarding the characteristics of flash droughts and the societal impacts, the value of the Evaporative Stress Index and Rapid Change Index data sets as drought early warning tools, and also on potential ways that access to enhanced drought early warning information would impact your decision-making process. If you're interested in providing your input to these questions, please complete the online survey at the web address provided on this slide. And then finally, more information about the Evaporative Stress Index, along with an archive of current and past conditions going back to 2000, can be found on the web page listed here. So with that, I'm going to end this webinar, and I'll take any questions. Thank you for your attention.
Thank you, Jason. Does any of the other presenters have any comments they'd like to add?
I think Jason did a very good job summarizing the current status of the ESI. So thank you, Jason. This is Martha Anderson.
Thank you, Martha. Does anybody have any questions? Feel free to type in the chat box if you do.
Hi, this is Mark Schaefer. I'd also like to mention in one of the stakeholder meetings that people were really exploring other options in terms of water management, maybe potential early deployment for fire management resources and things like that. So the potential, while this focused on the crop and rangeland management, may be far greater than what we had initially anticipated.
This is Martha again. I'll also add that we're showing here on this web page ESI maps over the continental United States, which are being generated in real time. These maps will be extended to all of North America in a very short-term period. We're also generating ESI maps over some other continents, and not quite in real time yet over South America, to look at yields in Brazil and other countries there, and also over Africa, to assist in some index insurance programs and yield monitoring there.
Yeah, and this is Mark Svoboda here, also one of the participants with Jason and Martha and others on this team. And as we're waiting for questions to roll in, one thing I just wanted to add was, you know, we really see these sorts of potential tools as pretty exciting additions to the drought monitor. You heard Jason allude to a lot of comparisons on the lag of the drought monitor responding to these quick droughts or flash droughts. And this was the motivation behind integrating these sorts of tools into the drought monitor process, because the Farm Bill policy is tied to the drought monitor. We want to become more responsive and augment the data that we look at that are more climate-based. And this is a physical system-based, evapotranspiration-based tool that sort of fills a really much-needed gap in our drought monitoring capacity. So I'm pretty excited by this, and there's some other new tools coming online, hopefully in the next year or two, that will fill other niches, if you will. So thanks for that presentation, Jason.
Welcome.
We'll see if anybody else has any more questions or comments. Well, as a reminder, this webinar is being recorded and will be posted to our SCIP homepage, southernclimate.org, if you'd like to refer back to it or share it with other folks. And I'll send out a notification when that is ready. It looks like Wendy has a question. Do you have any idea how much the one category degradation week has on the USDM lag? And would this allow for more than one category per week?
That might be a question for Mark Svoboda.
Yeah, I guess I'm on the hot seat there, since I do wear the drought monitor author hat, and in fact I'll be doing it here in early May. I think what you'll see is probably allowing for more than a 1 cat a week degradation, which, you know, Jason alluded to some of the critical windows in a crop's particular growth cycle and how it differs between corn and soybeans, and obviously it's really different for something like winter wheat. But we have seen some actually really hot, dry conditions going back to that 2011 year and even into 2012, early in the year, like really record high temperatures in February and March, even in the Southern Plains, and most recently in March up here, that have really had impacts on winter wheat conditions as well. So where I see more potential for this is that we're not 4 weeks behind the curve on ramping up. We typically don't like to jump 2 or 3 categories as far as degradation is concerned. Where you will see multiple category changes is usually on the improvement side, with tropical storms or hurricanes that can come online and dump copious amounts of rain. You might see something go from a D3 or D2 down to D nothing or D0. When you're going into drought, with tools like this, I think it should help us avoid multiple category changes. Whereas now, you know, you feel like you're catching up, like you feel more pressure to go, hey, we're 2-3 categories behind here. So tools like this, I think, will keep us ahead of the game, keep us ahead of the curve, and hopefully not lead to those multiple categories, especially on the degradation side. So that's a very good question, Wendy.
Great. Unless there's any other questions, I'm going to say a big thank you to Jason Otkin and the other presenters and participants who were here this afternoon. As I said a minute ago, this webinar is being recorded, and we'll post it to our SCIP YouTube and as well as our website once it's available. I'll also send out a notification just as I did for this webinar announcement. And in that notification, I'll include the links to the survey for the ESI drought monitoring, and then also more information on the evaporative stress index as well, the 2 links that were provided here at the end. Drought status and outlook briefings that we do, 5-minute briefings, are updated on Thursdays following the release of the drought monitor map. And those are also uploaded to our SCIP website and our YouTube either Thursday afternoon or Friday morning for more information on that. If you have any questions or need assistance dealing with the drought or other types of hazards, please feel free to contact us at SCIP. And unless there's anything else, we thank you for your time today, and we look forward to continuing this conversation with you in the future. Thanks.